Hello everybody and welcome to the last lesson on chapter 2. Today we're actually going to finish off the derivatives quote-unquote portion of the course. Of course we're still going to be doing derivatives, but it's going to be in a different fashion. So today our class will be on different rate of change problems. As you might have noticed by now, derivatives and rate of change go hand in hand because the first derivative is literally just a rate of change problem. So on that note, we will actually going to cover business functions and then some other rate of change problems that are not that big, but I still want us to go over just in case they appear on your tests and stuff like that. So let's get started. So what are business functions? Well, let's just think about it. Mathematics plays a huge part in business, right? You can't sell anything without knowing math. Like if you sell an apple for $5 and you don't know that 0 plus 5 is 5, you're not going to get anywhere. And so some really good mathematicians have come up with different mathematical formulas and functions to represent different activities and concepts that occur within businesses. So today we're going to take a look at 4 main functions that I have listed down below. So the first function we're going to learn is the demand function, which is also called a price function. So P of X, or P, is the number of units of a product or service that can be sold at a particular price X. So if I have 5 apples, right? And I have a price of $10 per apple. Like these are golden apples you get in Minecraft. Like you don't want to let them go, $10 per one. They're that expensive. We could create a demand function from it. So then what is our price? Our price is 10, P is 5. So then for using that, we could figure out that P of X is equals to 50, right? That is the total price that we could get. Similarly, moving from the demand or the price function, we go into the cost function. If I want to sell a Minecraft apple for $10, right, I need to realize I need an apple and I need some gold. Gold ain't cheap. Breaking a tree and getting the chance of an apple falling down is also ain't cheap. Like this requires labor, and so those costs must be accounted for. And that is why we have the cost function. The cost function, C of X, is simply the total cost of producing X units of a product or service. Again, if we talk about selling golden apples, our cost could be something like $7.50, right? It could be like a $5 flat fee plus $1 per apple sold. In that case, our cost function would be 5 plus X. So when you hear about these different functions, you need to understand that they don't necessarily just talk about P of X and C of X. They actually require you to read in between the lines and gather information. So moving on from that, we have the revenue function. Now that we figured out the price function and the cost function, we can actually generate some revenue, right? So revenue is the total income from sales that you'll gain when you sell some product or provide some service. So now the demand function said I could sell them for $10. I sold all 5 of them, right? My total revenue is 50, and that is a revenue function. Again, I'll give you a proper example on the next page. However, right now I just want to give you the basics. So when we're talking about the revenue function, all you need to remember is this equation here. So the revenue is equals to the amount of units you have times whatever you determined as your price. Your price could be calculated based on how much you want to charge, right? And you could, for example, inflate that depending on how much you sell, which is why it is a function. It could be a constant. It could be like 2. All of my apples always cost $2. But if you want to be fancy and you want to say that only small apples cost $2, but per gram of match that they increase to charging an extra cent, that would modify your price function and thus modifying your revenue function as well. Lastly, we have our profit function. The profit function is the total profit from sales of the profit function depicts the total profit you get when you sell X units of a product or provide some certain amount of service. The profit function is the difference between the revenue and the cost function. As you can see, that's not a minus, that's a asterisk. So let's go fix that. There you go. So again, you encountered these types of functions in grade 10, maybe grade 11, maybe even grade 9. Those very simple type of problems, they're still here. We just now are dealing with more complex numbers, and that's why we need to go over them again. Another main topic that we need to understand is that all these 4 functions are very useful by themselves, right? Like you could run a business pretty well. Like you could keep track of its finances using these 4 functions. But if you want to be actually involved and understand how your sales are going and make predictions off of them, that's when you'll have to use derivatives. Since the derivatives of each of these functions will actually provide you other essential information that is useful for a business. So what are these derivatives? Well, the C prime of x is called the marginal cost function, and it refers to the instantaneous rate of change of total cost with respect to the number of items produced. So again, if you have a production level of, let's say, $10 apples a week, right? And then you notice that a lot of your customers are asking for apples, and you're like, maybe I should increase it depending on how many sales I get, or like how many times I sell. So the rate at which you would increase it at could be found by the marginal cost function, right? The cost covers how much you're spending on producing these apples, which is extremely useful if you don't want to waste your money. Like you don't want to buy 1,000 apples if you're only going to sell 30, which is why you should increase only by how much the function tells you to. The next function, or the derivative I should say, is R prime of x, which is called the marginal revenue function, and it refers to the instantaneous rate of change of total revenue in respect to the number of items sold. Again, if you want to see how well you were doing at 100 sales compared to 200 sales, you could find the average rate of change, right? But if you want to know what would happen if I sold exactly 150, finding the instantaneous rate of change of your revenue would let you do that. The last part we have is P prime of x, which is the marginal profit function, and that one refers to the IROC of the total profit with respect to the number of items sold. All of them go hand in hand with each other, as you might have noticed. The only one that doesn't have a derivative associated to it is our price function, and that's usually because your price might be defined as a constant, and in that case it would be 0, and that's not really a good idea, right? Like you would want it to be something more interesting. Either way, if you're asked to find the IROC of your price, you just need to find the first derivative. Everything here is just revolving around finding the first derivative. With that being said, the whole process itself is very simple, but it could be pretty tedious if you don't know the information you're looking for, which is why I want to take up a question together with you guys so that we all get the needed experience in solving these types of problems. So the problem I have is this one. We're given a cost of producing X hot tubs, and it's represented by this function here. So we have 2 terms, right? And then we just have a restricted domain. We need to find out the answer to these 5 questions, and in order to do that, I will open it in Notebook and show you how to do them. Okay, so here I copied down the question, so let's get to solving it. In part A, we're asked to determine the marginal cost at a production level of 750 hot tubs, and then we need to explain what it means. Well, immediately, marginal, as you might have noticed, everything that says marginal means the derivative. Therefore, we're trying to find the derivative of our cost function, which is c of x. So, what is c prime of x? Well, c of x is equals to 3,450x minus 1.02x squared. We have 2 parts here, separated by division, which is pretty easy to do. So let's do that. So over here, c prime of x. Look at our first term. We have a constant times a single variable, right? This has a power of 1. So when we find the derivative of it, it's simply 3,450. This one's a little bit more complicated, but using the power rule, we know that the 2 gets multiplied by 1.02. Then the power gets decreased by 1, which leaves us with just x. If you want to simplify this, then we would get 3,450 minus 2.02x. Since we're searching for 750 hot tubs, we substitute that into for x, and we get our final answer, which in our case will be $1,920, right? Because this was given to us in dollars, as it says above. There you go. For part B, we're asked to find the cost of producing 751st hot tub. Well, that is very, very easy as well, because now we need to figure out how the 750th hot tub is related to the 751st. Well, clearly what we could do is just substitute c of 751, right? That would be your first instinct, but as you may realize, this means that we're finding the cost of producing 751 hot tubs, not the 751st hot tub. So if we want to find its actual cost, we would have to find the cost of 751st hot tub minus the cost of 750 hot tubs, right? Because then we would cancel out the first 750, leaving us with the 751st. So if we were to do that, we simply just substitute everything into our equation here, right? So we would have 3,450, 751 minus 0.2 times 751 to the power of 2. Then we would take this whole thing and subtract 3,450 of 750, and then again 0.2, 750 squared. Now if you put this into your calculator, you should get something along the lines of 1,918.98, which is $1.02 less than the 750th one. So what does that mean? Well, for part C, we could see that it's clearly less, so we could either assume that it's going to continue becoming less, or at some point it will turn back up and the cost will continue to rise. However, it doesn't seem that we are too concerned about that at the moment, so let's move on to part D. Each hot tub is sold for $9,200. We need to write an expression that represents the total revenue from the sale of X hot tubs. Well, that's very simple, right? Revenue was the price times the amount of units you sell. So what is our price? Well, our price is 9,200, and so our revenue function is 9,200x. For part E, we need to determine the rate of change of profit for the sale of 750 hot tubs. That is where some people also might get confused. But first, let's erase everything here so that we don't have an eyesore to look at. But when we're talking about profit, you need to remember that it is equals to the difference between your revenue and your costs. So again, P of X, so the profit function is equals to your revenue function minus your cost function. We just determined that our revenue function is equals to 9,200x, and our cost function was given to us at the top, and that is equals to 345x minus 1.02x squared. So let's put these two together. So P of X is equals to 9,200x minus 3,450x plus, because remember, two negatives make a positive, 1.02x squared. So now we have this. We could combine the first two terms, right? Because they only have a single x. So if we do that, we get 5,750x plus 1.02x squared. We were asked to find the rate of change of profit, which would mean that we need to find P prime of X. Luckily for us, this equation here is very, very simple. Again, we have a constant times a variable with no power, or with the power of 1, so that just becomes the constant. Then we have x squared, so we put the 2 in the front, leave the 1.02, then we decrease the power by 1, so we have x to the power of 1 now. So if we want to simplify this, we get 5,750 plus 2.04x. Now, again, 750 hot tubs. So let's substitute that number in. So P prime of 750 is equals to 5,750 plus 2.04 times 750, which is equals to $7,280. And so the rate of change of profit for 750 hot tubs is $7,280 per hot tub, which is quite a lot of money. So as you can see, these types of questions don't really take a lot of knowledge to do, but you need to know how to read an equation or a question very quickly and identify the key points, such as the restrictions, the marginal cost. So if you see marginal, that means derivative. Again, any numbers usually tell you key information, and then also locate where your variables are present. So for example, again, 750 here, then rate of change also means derivative. So now, in your next question, if you see something like this, simply scan for those values. You could also scan things again for X and things, for example, like dollars, because units are also very important, but usually you don't really see cents or like write it in thousands, but sometimes that does happen. So make sure you actually go over the question if you have time, or if you, once you're scanning it, just like try to identify the units that you'll be working with. So hopefully that little example has shown you how you could apply those different business functions and quickly do them on the fly. Now that we're done talking about business problems and business functions, we can move on to other rate of change problems you might encounter within chapter 2.6. These three came directly from the example page and the before questions in the textbook. So I wanted to go over them just in case you don't want to read those long pages of explanations. The first one that we need to cover is called kinetic energy. If you took physics, you know exactly what this is. If you didn't take physics, don't worry, I'll explain to you as simply as I can. Kinetic energy is energy produced by something that is moving. So if you are moving, you are producing some power, right? That power we call energy. And you could calculate that energy by the formula over here. K, which is our energy, will be written in joules, which is a big J. M is the mass of an object in kilograms, and V would be the velocity of the object in meters. So now you could solve for kinetic energy whenever you're given M and V, right? Usually M will be a given, and then your velocity would be changing, right? Because as we learned about velocities, they usually don't stay constant, especially not in calculus, and like grade 11 physics they do. But just taking chapter 2.3 as an example, velocity was never constant there. So with that being said, this chapter will require you to find the rate of change of kinetic energy at a specific time interval. Again, whenever you hear the words rate of change, the first thing that should come to your mind is derivative, okay? The first derivatives will give you the solution to any instantaneous rate of change problem. Instantaneous means at a specific point, and thus that would be the solution to our question here. Sorry about that scrolling. The second problem you might encounter is revolving around electrical currents. Again, another topic from physics. What wonderful news. Again, if you don't know, electrical currents can pretty much be studied very simply from the Ohm's law, which I said over here. You have 3 different variations of this, but in case you didn't know, R would be your resistance, V would be the voltage, and I is the current. You measure these in different things. So V is in volts, I is in amperes, and R is in ohms. So in case you don't know that, I heavily recommend you search this up and like print a cheat sheet so you remember it until your test comes. If you don't remember it, then just do a lot of questions like this, just so you remember what different units come with these variables. So again, when you use the Ohm's law, you are going to be required to find the rate of change in resistance, for example, in respect to some current. Since it said there's 3 different variations of this law, you could get a combination of any 2 of them. So rate of change of voltage compared to the current, the rate of change of current compared to the resistance, stuff like that. Either way, rate of change is the derivative. So if you could make the equation above, right, if you're given one of them, you can express it and then find the derivative of that equation. The last one is pretty interesting, and it's called linear density. Linear density refers to the mass of an object per unit of length. So again, linear density is just equals to mass divided by length. So that could be kilograms per centimeter, could be pounds per foot, if you are American, but either way, the equation stays the same. These types of functions occur usually when working with strings and wires, because the problem arises when you're mixing different compounds together, right? If you take a piece of copper, right, and you make it into a coil, all throughout it's going to be copper, and the density should be around the same, right? However, if you get just a random spring or a random coil you find in a pen or something, right? That's usually an alloy of different metals and different compounds. And so if you wanted to find the density of it at a certain distance, right? Like for example, if it's 10 centimeters long and you want to find the density at 2 centimeters, there's no guarantee that that point right there will be copper or iron or anything of that. It could be a mixture of different things, which is why linear density is important. So, suppose you're given the function f of x, and it gives you the mass in kilograms of the first x meters of the object. So, again, a 2 meter spring, for example. That's x is equals to 2 in this case. Then, for some part of that object, right, you have distances between x1 and x2. You could choose any point you want. You'll usually be given to you in the question, so don't worry too much about that. If you want to find its average linear density, or the mass per unit of length, you would have to find the difference between the values at x1 of f of x at x2, and I'll divide that by the distance between those 2 points. If you want to find the rate of change of density at a particular length, you would have to then find the derivative of the function f of x. This is the function f of x, and these are 2 points, x1 and x2, so don't get that confused. Again, this sounds a little bit complicated because there's so many of the same variables everywhere, so let's do a simple example. The mass in this case is given in grams for the first x meters of a wire, and it is represented by the function f of x is equals to the square root of 2x minus 1. We need to determine the linear density at x is equals to 5 and x is equals to 8, and then compare the two densities at the points. So f of x, again, is equals to the square root of 2x minus 1. We should rewrite this, right, because we know how to work with powers, and the square root is simply to the power of 0.5. So once we do that, we can move on to the derivative. And so over here, we said that p of x is the same as the derivative of prime of x. I just used p of x since it's easier to write. So if we're given this, what should be its derivative? Well, it's pretty simple, right? The product, this is a power, bring it to the front. Then we have 0.5 here, and then 0.5 minus 1 is negative 0.5. However, using the chain rule and the special case, remember we need to take the derivative of the outer function, which we already did, but also the derivative of the inner function. So what's the derivative of 2x minus 1? The negative 1 we don't care about, it just becomes 0, but 2x, the derivative of it is simply 2. So we need to multiply 0.5 times 2x minus 1 to the power of negative 0.5 by 2, which would simply cancel out the 0.5 and the 2, which is why we simply have 2x minus 1 to the power of negative 0.5 as our function. Since we're given the points 5 and 8, we substitute those numbers in and solve. So we get a third and then 1 over the square root of 15. So, as you can see, the density has tremendously decreased from 5 to 8, right? Because a third compared to the square root of 1 over 15 are very different things. The square root of 15 is around 4. So 1 over 4 is 0.25, and a third is 0.3. And as you can see, it has clearly decreased. So if you're good with these types of questions, then you should have no problems in finishing off chapter 2, because we're already done with 2.6. So in case you want some extra work, here is 4 questions. They all have various parts to them, so don't take them too lightly, but they shouldn't be anything difficult because again, they're all just rate of change problems. I'd like to thank anyone who has stayed around till the end of the video. You guys are truly awesome, and I can't wait to see you guys next time. Bye bye!